Hello students. Welcome back to class. Today, we are moving into part 3 of electric fields. But before we get started, let's take a moment to review what we learned in our previous lesson. In our last class, we discussed the properties of materials that resist the flow of electric current, such as rubber and glass. In contrast, we also looked at conductive materials like copper and aluminum, which allow electric current to pass through easily. Additionally, we explored the meter bridge and illustrated its structure with a diagram. The goal for today is to explore the concept of electromotive force, EMF, and potential difference. Our first objective today is electromotive force, known as EMF. This is the maximum potential difference across the terminals of a cell when no current flows, indicating how much energy the cell provides to move charge around the circuit, and it is measured using a voltmeter. On the other hand, potential difference, known as PD, is the voltage measured across the terminals of a cell when it is delivering current to an external circuit. And it is always less than the electromotive force EMF due to the energy lost overcoming the cell's internal resistance. Let's explore the difference between electromotive force, EMF, and potential difference, PD. These are two important concepts in electricity. Definition: EMF is the electric force or energy supplied by a cell or battery to move charges through a circuit. PD, on the other hand, is the voltage measured across components when current flows through them. Presence of current. EMF exists even if no current is flowing, such as in an open circuit. PD becomes zero if there is no current flow. Relationship: EMF is the cause, while PD is the effect. The battery creates EMF, and as current flows through a circuit, PD is observed across resistive elements. Unit and symbol: both EMF and PD are measured in volts. EMF is usually denoted by E, and PD by V. Dependence on resistance: EMF does not directly depend on resistance, while PD depends on external resistance. Understanding these differences will help you analyze and solve electric circuit problems more confidently. Example: a battery or cell is a source of EMF. A light bulb glowing due to a voltage drop is an example of PD. Let's look at the key equations. The potential difference V is equal to the electromotive force E of the cell minus the voltage loss due to internal resistance, IR, where the terminal voltage V is the voltage available across the cell. E represents the electromotive force EMF of the cell in volts. I is the current flowing through the circuit in amps. R is the internal resistance of the cell measured in ohms, and V is the lost voltage. The electromotive force E is equal to the current I multiplied by the total resistance, which is the sum of the external resistance R and the internal resistance R. The current I is equal to the electromotive force E divided by the total resistance, that is, external resistance plus internal resistance. The lost voltage, also called the voltage drop inside the cell, is equal to the current I multiplied by the internal resistance R. Let's solve an example. A battery is made up of two cells. Each cell has an electromotive force EMF of 1.8 volts and an internal resistance of 2 ohms. The battery is connected in series to an external resistor of 6 ohms. You are required to calculate: 1. The total current flowing through the circuit. 2. The potential difference. 3. The lost voltage drop across the internal resistance. Solution: we are given number of cells equals 2. EMF of each cell equals 1.8 volt. Internal resistance of each cell equals 2 ohms. External resistance equals 6 ohms. Let's solve the problem step by step. Step 1. Total electromotive force and total internal resistance. Since the two cells are connected in series, the total electromotive force is the sum of the EMF of the individual cells. Therefore, the total EMF is 1.8 volts multiplied by 2, which gives 3.6 volts. Likewise, the total internal resistance is the sum of the internal resistances of both cells. This is 2 ohms plus 2 ohms, giving 4 ohms. Step 2. Total resistance in the circuit. The total resistance in the circuit is the sum of the external resistance and the internal resistance of the battery. That is 6 ohms plus 4 ohms, which gives a total of 10 ohms. Step 3. Calculating the current. Using Ohm's law, the current is equal to the total electromotive force divided by the total resistance. That is, 3.6 volts divided by 10 ohms, which gives a current of 0.36 amps. Step 4. Calculating the potential difference. The potential difference is the voltage across the external resistor, which is calculated by multiplying the current by the external resistance. That is 0.36 amps multiplied by 6 ohms, which gives 2.16 volts. Step 5. Calculating the lost voltage. The lost voltage is the voltage drop across the internal resistance of the battery. It is calculated by multiplying the current by the total internal resistance. That is 0.36 amps multiplied by 4 ohms, which gives 1.44 volts. Final answers. The total current flowing in the circuit is 0.36 amps. The potential difference is 2.16 volts. The lost voltage across the internal resistance is 1.44 volts. You've completed this lesson, well done. Put your knowledge to the test by trying these questions. They are a great way to deepen your understanding of the topic. In summary, we explored electromotive force EMF and potential difference. I hope you found the class both enlightening and engaging. In our next lesson, we'll move forward with electric field, part 4. Thank you.